Hello children, today we will start the first chapter of class 9th, which is number system. But before starting that, we will talk about a few mathematicians, and the first among those is Pythagoras. You all have heard his name. About 400 BC, he discovered that square root is an irrational number because it cannot be written as P upon Q. And around 1800, two German mathematicians, G. Cantor and R. Dedekind, they discovered that corresponding to every real number, there is a point on the real number line, and corresponding to every point on the number line, there exists a real number. It just sounds difficult, but actually it is not. It simply means that all the real numbers can be represented on a number line. And its inverse is also true, that all the points on a number line represents one or the other real number. Now let's talk about Archimedes. You must have heard his name also. This Greek genius was the first to compute the numbers in the decimal expansion of pi. We all know that pi is equal to 22 upon 7, but actually that's not true. The actual value of pi is a little more or a little less than 22 upon 7. So he was the first one to compute the digits of the decimal expansion of pi. So now we are ready to start our chapter, number system. So let's begin. So try to think and tell me about the beginning of the number system. There are many stories about it. Some people believe that a shepherd invented this system to keep a count of his sheep. Some other believe that this system was invented by a hunter to keep a record of his huntings. Their techniques of counting were also varied. Some people say they used to count with the help of fingers or by drawing lines on a surface. Some used to count by tying knots in a rope or a thread, while others used to keep a number of pebbles with them equal to the counting they wish to remember. That's interesting, isn't that? But with the invention of written script, they started using different symbols and signs for this purpose. And over the time, these symbols and signs got changed again and again, and gradually we got the number system which we use today. So let's start with it. It begins with natural numbers. Nature. What has nature given us? If we see nature, then there we have trees, plants, flowers, leaves, birds, animals, moon and stars. If we try to count any of these, then from where shall we begin? We will begin from 1. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 makes 4. Thus, by adding 1 to each number, we get its successor number. 10, 20, 30, 40, 100. How far can these numbers go? What do you think is the biggest number? So think of a big number which you think is the biggest of all and keep it in mind. Now, if I add 1 to it, I will get a new number and my number will be bigger than yours. So, we can say that there is no such number which we call as the biggest. The numbers are endless. So, we write n equals to 1, 2, 3, 4, 5 and they go till infinity. They never end. So, we denote infinity with this symbol. Now comes the whole numbers. Just as we get the successor of a number by adding 1 to it, in the same way, by subtracting 1 from a number, we get its predecessor. Let's do it. See, here is a basket. And what is there in the basket? Balls. Can you count the balls? Yes, there are 5 balls. Now, if I take away one ball, what will be there? there will be 4 balls. If I take away one more, then we get 3 balls. Taking away one more, we get 2, then 1. And if I take away this last ball also, then what do we get? Now there is no ball in the basket. So how can we denote this situation? We can write it with the help of a 0. Now there are 0 balls in the basket. Do you know where this 0 was invented? Yes, it was invented in India only by our mathematician Brahmagupta. And this invention made our number system a complete whole. Thus we denote the whole numbers with a W. Thus W equals to 0 plus all natural numbers. It can be written like this: W equals to 0 plus n. After this, when the exchange of money started, then a need was felt for negative numbers. Suppose I bought something for rupees 100. Now I need to pay the shopkeeper rupees 100. So how can I express my situation? My situation will be expressed with minus 100, negative 100, because there is a loan of 100 rupees on me. Now suppose I pay the shopkeeper rupees 70. So we can write minus 100 plus 70. I still need to pay him rupees 30. So I still have a loan of rupees 30, which can be expressed as minus 30. Such numbers are expressed by Z. On a number line, in the middle we have 0, and on its right side the numbers that are written are 1, 2, 3, 4, 5 and so on. Similarly, on the left side at equal intervals we write minus 1, minus 2, minus 3, minus 4 and so on. You must have also noticed the arrow on both the sides of the number line. It denotes that number line can be extended to infinity on both the sides. That is, infinite numbers can be represented on a number line. Thus, all these numbers taken together are called the integers. That is, integers equals to all negative numbers plus all whole numbers. Now, between any two numbers on a number line, for example between 0 and 1 or 1 and 2, does any number exist between these two numbers? Yes, endless numbers exist between them, and we call them as fractions. Now suppose there were two brothers. They bought a watermelon. They won't eat it all alone. So they shared it by dividing it into equal parts. So the total number of parts will be written as denominator, that is 2, and number of parts that each child got will be written as numerator, that is 1. So our fraction is 1 upon 2, which denotes 1 part out of 2. Can we express it on a number line? It is a half, so it will lie on the exact midpoint between 0 and 1. But now suppose there is some other division, for example 1 upon 3. That is, the watermelon was divided in 3 parts and 1 part was taken. Or if the watermelon was divided in 4 and 1 part taken, it will mean 1 upon 4. Now let's see some other forms of such fractions. 1 upon 2, or if we divide the watermelon in 4 equal parts and I take away 2 of it. So how can we express that? We will write 2 upon 4. If we observe carefully, we will find that actually 1 upon 2 and 1 upon 4 are expressing the same situation. In both the cases, half of the watermelon is being taken. Now if I want to express in some other forms like 4 upon 8 or 8 upon 16 or 16 upon 32, they all mean the same. All these are the fractions. But if I divide the numerator and denominator with a common factor and write these fractions in their smallest form, then these fractions will become rational numbers. This is how we identify a rational number, that is, which can be written in the form P upon Q, where Q is not equal to 0 and where P and Q are co-prime. That is, there exists no other common factor of P and Q except 1. Rational numbers can be positive as well as negative. Rational numbers are also of two types. If we divide them and look at their decimal expansion, we will see that a few of them have a terminating decimal expansion. That is, if we perform the division, then it ends somewhere and we get the remainder as 0. While some other rational numbers are such that when we divide them, the division never ends. That is, we never get a 0 as a remainder. So what happens is 1, 2 or more numbers, they start repeating themselves in the quotient. So such rational numbers are said to be having a decimal expansion which is non-terminating, repeating. Non-terminating because it never ends, and repeating, it means that few of the numbers have started repeating themselves. Let's look at some examples. 11 upon 5, 1 upon 2 or 1 upon 3. If we divide 11 by 5, we get 2 decimal 2. So it has a terminating decimal. Similarly, on dividing 1 by 2, we get 0.5. Thus, it also has a terminating decimal. But 1 upon 3. On dividing 1 by 3, we get 0.3333. Thus, 3 will keep coming repeatedly. To express it, we write it as 0.3 bar. This bar suggests that it is a non-terminating repeating decimal. Can you find out without actual division that which of the rational number has a terminating decimal and which has a non-terminating repeating decimal expansion? It's very easy. Let's see how. We will do it with the help of a few examples. Like 1 upon 2, 1 upon 3, 1 upon 5, 1 upon 7, 1 upon 10 and 1 upon 15. Now let's see their decimal expansion. On dividing 1 by 2, we get 0.5. On dividing 1 by 3, we get 0.333. By dividing 1 by 5, we get 0.2. Dividing 1 by 7, we get 0.142857. And it keeps on repeating. By dividing 1 by 10, we get 0.1. And on dividing 1 by 15, we get 0.06666. It is also repeating itself. Thus, we see that 1 upon 2, 1 upon 5 and 1 upon 10 have a terminating decimal, while 1 upon 3, 1 upon 7 and 1 upon 15 have a non-terminating repeating decimal. Now, let's look at their decimal expansion once again. By looking carefully, we will find something new. Look at the denominator of all these numbers. If we write these denominators as a product of their prime factors, and if we write the prime factors in exponential form, we will find that the rational numbers whose denominator has the prime factorization as any power of 2, any power of 5 or any power of both 2 and 5, then such rational number has terminating decimal expansion. While the rational numbers whose denominator's prime factorization includes any number other than 2 and 5 will have a non-terminating repeating decimal. I have taken very few examples here, but you can try this with some more examples of your own. So these were the rational numbers. Now let's have a look at the irrational numbers. Irrational numbers are those which are not rational, that is, which cannot be expressed in the form P upon Q. For example, under root 2, its decimal expansion is 1.4142356 and so on. It never ends. Similarly, the decimal expansion of pi is 3.1415925 and so on. It also never ends. Let's have a look at another example. 0.10111110111110. On seeing this, we feel as if it is repeating itself. But that's not true. Because every time the number of times 1 appears gets changed. For example, once, then twice, then thrice, 4 times and so on. Our number line is complete in itself. All the numbers, that is natural numbers, whole numbers, integers, rational numbers, irrational numbers, all the numbers can be represented on our number line. So let's do it with the help of some examples. Our first example is 3. To show it on number line, what will we do? In the center we have 0. On its right at equal intervals, we have the first number as 1, then 2, then 3. Thus, this point represents 3. Now, let's take minus 2. For this, in which direction should we move? We need to move to the left of number line because this is a negative number. Minus 1, then minus 2. Okay, then for minus 3, for this we will need to move a little further, that is minus 3. Now 2. For 2, we will need to go to the right side of 0 again, as it is a positive number. 1 and 2. Next number is 6. For 6, we will have to go a little more on the same side. 1, 2, 3, 4, 5, 6. Now our next number is 1 upon 2. How can we show this on a number line? We have talked about it earlier also. At exact midpoint between 0 and 1, we can show 1 upon 2. We will also see some other easier ways of representing it a little later. So, our next number is under root 2, which is an irrational number. So, how can we express this one on a number line? So, come, let's look at the technique of representing an irrational number on a number line. But before doing that, we must know about the Pythagoras theorem. You all have done it in your previous classes, so you must be knowing it. For this, we need a right angle triangle. If the base of the right angle triangle is B and its altitude is A, then according to Pythagoras theorem, A square plus B square equals to the square of its hypotenuse. That means C square. This all you know very well. If yes, then we are ready to do it. So let's start. For this, first of all, we will take a number line. On this we have 0 in the middle. On right side we have 1, 2, 3, 4, etc. And on the left side we have minus 1, minus 2, minus 3, minus 4. Let's name 0 as O and 1 as A. Now the distance between 0 and 1, that is OA. So let's draw a perpendicular of length OA at the point A. It means we need to draw an angle of 90 degree at the point A in such a way that the length of this perpendicular is equal to OA. This is very easy to do. We can do it with the help of a compass. Open the compass equal to the length of OA. Now, taking A as center and radius OA, make an arc on the perpendicular. It will cut it on a point. Let's name it as B. Thus, OA equals to AB. Now, if we join AB, then we will see that we have got a right angle triangle in which OA is the base, AB is the altitude and OB is the hypotenuse. Thus, according to the Pythagoras theorem, OB square will be equal to OA square plus AB square. Now, as OA equals to 1 and AB is also equal to 1, thus OB square equals to 1 square plus 1 square. Thus, OB square equals to 1 plus 1, or we can say OB equals to under root 2. So, from here we conclude that the length of OB is under root 2. Now, if we want to represent this length on number line, then by keeping the compass on O and taking the radius equal to the length of OB, we can make an arc on the number line. Suppose it cuts the number line at C, then OC will be under root 2. Thus, we get a point C which represents under root 2. In a similar manner, we can represent under root 3 on a number line. For this, in the same figure, we will take OB as base and then draw a perpendicular to this base at the point B. It means we will draw an angle of 90 degree at point B. Now, the length of this perpendicular should also be made equal to 1 unit only. Thus, we get a point D. Joining OD, we will see that we have got another right angle triangle. We will also see that the length of OD square will be equal to OB square plus DB square. Thus, OD square equals to OB square, which is under root 2 square plus DB square, that is 1 square. So, OD square equals to 2 plus 1. Thus, OD square equals to 3 or OD equals to under root 3. Thus, we may conclude that the length of OD is under root 3. Now, keeping O as center and taking the radius as OD, we can draw an arc on the number line, which will cut it at a point. Let this point be E. So, now OE equals to under root 3. In the same way, we can depict the under roots of 4, under root 5, under root 6, etc. on the number line. Now, is there any easier way to depict rational numbers on a number line? Yes, let's see how. If we write the rational numbers in decimal notation, remember now we are talking about rational numbers. So, if we write them in decimal notation, then looking at the number line carefully, we will see that the distance between any two numbers on a number line has also been divided in several smaller equal parts. Let's look between 1 and 2. We will find that this distance has been divided in 10 equal parts, which can be written as 1.1, 1.2, 1.3, 1.4 and so on. So, can we express rational numbers with the help of these divisions of number line? Yes, we can. Let's see how. Suppose we have a number 2.25. That is, after dividing a rational number, we obtained 2.25 as its decimal expansion. Now, it can be conveniently represented on the number line. See, when we look at the distance between 2 and 3, we find its subparts, which are 2.1, 2.2, 2.3, 2.4, etc. Now, our number is 2.25. So, now we will look at the distance between 2.2 and 2.3, because 2.25 will definitely lie between these two numbers. We will find out that it also has been divided in 10 equal parts. That can be written as 2.21, 2.22, 2.23 and so on. So, from here we will move to 2.25, and this is the point that represents our rational number. Let us see another example now. Suppose our number's decimal expansion is 5.378. So we will look between 5 and 6. We will find the partitions as 5.1, 5.2, 5.3, etc. On looking at the distance between 5.3 and 5.4, we will see more partitions as 5.31, 5.32, 5.33, 5.34 and so on. We need 5.37. Thus, now we will look at the distance between 5.37 and 5.38. Look at their further divisions. We will find 5.371, 5.372, etc. So, our point will be on 5.378. In the similar way, you can also try this with some more examples. So, children, today we talked about the real numbers, which included natural numbers that start from 1 and go till infinity. Then came the whole numbers that begin from 0 and go till infinity. Then we talked about the integers, that include the numbers which are negative as well as positive, plus 0. Then came the rational numbers, which can be written in the form of P upon Q. We also know them with the name of fractions. They can also be negative as well as positive. And then we talked about the irrational numbers, under root 2, under root 3, under root 5, etc. Okay, so now let's look at some questions. There exist dash rational numbers between any two rational numbers, 1, 2, none or infinite. We saw that there are infinite numbers on the number line. So the answer is infinite. Pi is a dash number, natural, irrational, rational or whole. Pi is an irrational number. So children, this was our chapter number system. Now we will meet in the next chapter, and till then you keep on practicing mathematics. Thank you. Have a nice day.